today we're talking 2.5 proving segments, as segments and angles. We're mainly going to work with segments. This is video recorded live in period 2. So if you have any questions at all, feel free to chime in, and you'll be on the recording. If not, then as always, if you wait until the very end, I'll have a Q&A after this is complete. Some key terms before we kind of talk a little bit, because it is about segments. Okay. And some of the things that we need to make sure that we remember is about proofs. Okay. The reason that we're doing proofs is is a logical argument that uses deductive reasoning. This deductive reasoning is used in order to show that a statement is true. And if you remember deductive reasoning, okay, there's a statement that is made, an if-then statement that is logic, and then we somehow have to show that it has some type of truth to it. So we're using a proof system in order to do that. There are three main types of proofs. There's the two-column proof, which is the main one that we usually use. That's the one where you take and you essentially make a huge T-chart, and you list all of your items that you're trying to prove. There's a flow chart or a flow proof, which we don't use as much. And then there's also a paragraph proof. Paragraph proof is where you write your proof in a paragraph, just mainly explaining what you do. We also don't use that one as much in my class. For a theorem, just kind of as a reminder, it's a statement that can be proven true. Or that can be at least proven. So we're going to use some ideas that we have for theorems, maybe even a postulate if needed. A lot of it is definitions of things. And usually there's a helpful hint in the proof that helps us solve. Something happened there with there it is. All right, so let's kind of talk a little bit about what's going to happen next. So a two-column proof. There are 7 steps of the proof are shown. Complete the statement to prove that JM is perpendicular to LN. Okay, so here's our first thing that we have. It says our given. So it tells us that we're given that JKL, our angle, so this angle here, is congruent to MKL, our other angle that is here. When we're doing these types of proofs, very similar to what we did whenever we were solving equations, the first line is always our given. It's always our given. So if you look at what they've posted up here, angle JKL is congruent to MKL. It's given. And then something new, when we change from congruency to equality, or equality to congruency, this actually has a typo on it. This should just be equality. We call this the definition of congruency, or the definition of congruent angles in this case. So anytime that you change from equality to congruency, or congruency, like in this one, we had congruency, and now we're changing it to equality, we're using the definition of congruence, or the definition of congruent angles. The reason that we change it from congruency to equality is because with equality, we can use, in simpler terms, equality, we can use numbers. So if you look at example number 3, it tells us the measure of JKL and the measure of MKL is equal to 180 degrees. Okay. What vocabulary do you know that makes it so two angles that are side by side equal 180 degrees. Linear pair. So in this example, or in this one here, we're going to say definition of linear pair. Sorry, this is video recorded, just to let you know. So, okay, let's hold this question in particular on this. Can you give me like 5 minutes and then I'll answer this? But come back here in just a minute. All right. So next it says use the substitution property of equality to complete the statement. So now we're looking for the statement. And if you notice the statement that is next, it says 2 times the measure of angle JKL. Out of these two, we already have one measure of angle JKL. What could I substitute in here so that I can combine it to get 2 times the measure of JKL? Not 90. We don't necessarily know yet that it's 90.
Could you do like a bisect?
We couldn't necessarily do a bisect yet because we haven't proven necessarily yet that it's a bisect. Could we maybe say measure of JKL? You guys are gonna think that this is funny, but couldn't we also just say that this was also the measure of JKL equal to 180? Because now that we've substituted it in, now we have 2 times the measure of JKL.
Yeah, that's what I was trying to say. I said the wrong word, but like I was trying to say split. Like how?
Gotcha. Okay. So now that we've combined them, that would be something called combining like terms. And then if we divided, it says here the division property, we divide by 2, then the measure of angle JKL is equal to 90 degrees. And because that is equal to 90 degrees, we know that this is perpendicular. These are perpendicular. So we'll say definition of perpendicular lines. So why we do proofs? Some of you can look at this and see, oh, those are the same angle. They're congruent. It's equal to 90 degrees. Done deal. With proofs, you have to explain each mathematical step or reason. Very similar to what we did the previous day when we were solving, how we had to explain every single step. The only difference here is what you have to start with your given. You have to somehow find mathematically through geometry what you're proving, which in this case, we go from those 2 angles being congruent to the 2 lines being perpendicular through geometry. That's where it gets difficult, guys, because you have to remember all of the different geometry terms. Yes?
How come we couldn't change the measure of KL to 90 if we knew that both of the angles were going to be like equal to each other? Because if they're equal to each other, then they must have to be 90 if they're like equal to 180.
And that's one of the things that using this, we have to go through certain steps in order to say. We can't just look at it and be like, oh, I know that's 90. We have to mathematically use some type of proof or some type of theorem or even definition in order to get to that.
But it is 90, so why can't you just skip a few steps? It still gives you the same outcome.
I know it kind of does give you the same outcome, but for that specific example, I wanted you to name each individual step. Why don't we try example number 2, okay, together again. Try example number 2. Talk a little bit about it. Now, look at example number 2. What do you know from looking at that picture? What do you know about those 2 segments? They're congruent, okay? But we can't just say, oh, I see the picture and I know that they're congruent. We have to mathematically go through steps in order to prove that they are. So if we take and look at this first reason here, the first reason is always our given. So now I'm going to name this and say that the measure of LM is equal to the measure of NP. I went from congruency to equality. That's going to be the definition of congruence. Or the definition of congruent segments, whichever one you want to put. And if you notice, I'm going to actually skip clear down to here, this very last one, because that's always, our last step is always going to be our proof. Notice how they're both on different sides. What would you call that in order to go from one side to the other or switch back and forth? It's not reflexive. Reflexive is a good guess, but it goes along with those. There was reflexive. There was symmetric. Symmetric. Good. So now I'm going to say that the measure of NP is equal to the measure of LM using the symmetric property of equality, or POE. And then I go from equality again back to congruence for my last step. That is the definition of congruence. So we had to go into our symmetric property of equality, or we had to go to equality in order to switch them, and then we can go back into congruence. Do you want me to take you through the last example?
Yeah.
Okay, let me take you through the last example here, and then we'll talk after I shut the video off. So prove this property of midpoints. If you know that M is the midpoint of AB, prove that AB is 2 times AM, and AM is 1/2 of AB. Okay. So the first thing that we're looking at here is the given. What we are trying to prove at the very, very end is that AM is 1/2 of AB. That's what we're trying to get to. We know that because this is the midpoint, what do we know about the two segments? If I said to you that AM was congruent to MB, that would be because of what definition? What terminology are we already using? Midpoint. Good. I heard somebody say midpoint. We're already using midpoint. So in this case, this would be considered the definition of midpoint. And then in order to kind of go through this, if you look, it's gonna we're trying to prove equality. So I'm gonna switch this to equality. I'm gonna say AM is equal to MB. That's the definition of congruence. So AM and MB are both equal, and they make that line, okay? If you look here too, we also have this, the AB. So how do we know AM and MB let me write it as this way. AM and MB, or plus MB, are equal to AB. What is that?
I have a question.
Okay.
Why is it the definition of congruence when it's equal?
So when it's the terminology that's used to describe when you go. The question was, why is it the definition of congruence when it's equal? The definition of congruence is the terminology that we use in order to go from congruence to equality, or equality to congruence. Every single time you always use that same terminology. Yes.
Segment addition.
Segment addition. Okay, so this is our segment addition postulate. We took two parts of the segment, created the whole. So segment addition postulate. So if I were to name AM twice, what did I do from the AM plus MB equals AB? What did I do in that step? What property did I use? Yes?
Substitution property of equality.
Good. So we use substitution. Property of equality. So now I can combine them. 2AM is equal to AB. We combine like terms. And then we use division property of equality to move the 2 over. And that is all for today.